Hi,
Hello, how are you?
tired.
Hello, hello. I just finished one of my lab finals today and went better than expected. Like I was kind of nervous for it, but it went well. Yes, it's good. Yeah. So we'll do 118A first, and then we'll do 118C later. I got the problems that you sent me, Alicia, and then we'll do H&M practice afterwards, and then we'll do the 118C questions that Camilla sent and the reactions as well. Okay, so let me share my screen here. Yeah. Oh, you covered HNMI in class today. Did she go over like everything like integration, coupling, neighbors, n plus one, de-shielding, shielding, degrees of unsaturation, the region, and then how to like approach it, like degrees of saturation, like predicting the product as well. That's good. That's good. Did it make more sense too?
I think how she was drawing it was a little bit more simpler.
Uh-huh.
But I think how you went over it was a bit easier.
Oh, I see, I see. Like the way that she hand draw all of the peaks out, like the sub peaks and neighbors and everything like that?
More so like she kind of drew it as like by groups. Like she kind of
Uh-huh.
drew like for an example, if it was like a CH3 and it had two neighbors, she would draw
Uh-huh.
like she would use up a neighbor like and like
Mm.
demonstrate it as like N and then drew it as like a bond. And then she kind of like did like a subtraction
Uh-huh.
thing to
Yeah.
like see how many bonds is used up.
Mm-hmm. Yeah. And if you do like ask different tutors as well, they're gonna have like different approaches to how they solve HNMR problems. Like or even different
Yeah.
professors as well, like Wei, Levens, Helix, Farhat, like they do HNMR very differently.
The thing was at AATC,
Uh-huh.
at least today, like mm, like almost a whole table filled up with HNMR, and that like every time we raised our hand, like
Yeah.
the tutors were like, "Oh, is it HNMR?" And they're like,
Yeah, I
"Yes."
know,
They're
I
like,
know.
"Oh, sorry." Like it's just a really hard topic to cover, which is understandable. But yeah,
Mm-hmm. It is. That's the hardest topic to tutor or teach, HNMR.
yeah. But your old the one of the dudes who's the a tutor now, he's pretty good at explaining it.
Yeah.
The one I
Aniket.
always yeah him.
Uh-huh. Yeah.
Yeah.
That's good. Right. Let me know if my audio is cutting off because I'm connected to my home Wi-Fi right now. So if it's cutting off, I'll switch to my other Wi-Fi. Uh-huh. Okay. So is there any specific problem that you wanted to go over here, Alicia?
Yeah, like more of the synthesis problems. I think
Mm.
there were a few like those ones. Those ones
Mhm.
are kind of hard to like
Yeah.
interpret.
These look exactly like Levin's problem sets. Did she copy these from Levin's problem sets
I have no idea.
118A?
She didn't really say.
I see. I see. Okay. Yeah, I think this is exactly what Levin's 118A problem set. Yeah, yeah, this one definitely is. This one, yeah, so this is copy and pasted over to Levin's 118A problem set. Yeah, it is copy and pasted. I also have the key for these as well. I'll send it to you for you to check after. But let me show you how to approach these first. Right, so let's look at the first one here. Okay. So this synthesis problem here, we start off with a cyclobutane, and we want to get into um, this product here with an alcohol attached to it, right? So in synthesis problems, what we could do is we could think about it backwards or forwards. It depends on the synthesis problem. But in this case, we can also look at the differences and similarities between the reactant molecule and the product molecule. So in this reactant here, we have a ring. In the product here, we have an open chain. That's not a ring, right? So this is one of the reactions you learned. It might not come up right now, but do you know what reagent we could use to open up this cyclobutane into a four carbon butane like this. It's okay if you forgot, but do you
Is
remember?
it
Uh-huh,
is it H2 or
uh-huh.
PD?
Yeah, H2PD, right? H2PD is the reducing agent that would reduce this unstable ring with a lot of ring strain into this butane ring chain right there, right? And I'm gonna highlight that butane ring like this in yellow, which is going to be this butane ring right there in yellow, right? That's gonna be the exact same group right there, the similarity. Now our new groups here that we're adding is going to be this alcohol and this ethyl group, right? So this is a regular boring alkane molecule here, and we can only do one reaction with that alkane molecule. It's the very first reaction you learned. What do you think we could do to this alkane? We could only do one thing here.
SN2?
SN2. SN2 is going to be needing a good leaving group, right? We require a good leaving group to do SN2. There's no good leaving group here. No halogen, no OMS, no OTS, no good leaving group, right?
So SN1.
SN oh yeah, so all of the reactions, SN2, SN1, E1, E2, they all need a good leaving group. Right? They all need like a
Oh,
bromine or chlorine, but there's no bromine or chlorine here. So we can't do any of those. We can do SN2, SN1, E1, or E2. But what can we do to add a good leaving group there? Let's say, like what can we do to add a bromine at the second carbon, let's say. There is a reagent that we could use to add a bromine on the most substituted carbon. Let's say here, bromine.
mm.
Right.
Was that chlorination
Yeah,
or
halogenation, but in this case,
yeah?
bromination. Right.
Mm-hmm.
You could do chlorination if you want, which in this case I would do chlorination because, or actually you could do either or. You could do bromination or chlorination, but in this case I'm gonna do bromination because it will selectively go for the most substituted carbon, which is either this carbon or this carbon here, right? So that's gonna be Br2 and light, which adds a bromine at the most substituted carbon of the alkane here, which is that carbon. Now we have a good leaving group here, bromine, right? Um, now whenever you see an alcohol and new R group right here, what reaction do you think of? What reaction do you think of when we try to add carbon-carbon bonds? It's one of the newer reactions. One of the newer reactions.
Is it a Grignard?
Uh, a Grignard reagent. Yes, that's right. That's right. It's Grignard reagent. That would add the carbon-carbon bond. But I just realized something here. Right.
Mm-hmm.
Notice how here the alcohol is on this carbon right here, which I'm gonna color code in pink. Right. If we go backwards right here, that alcohol will come from a carbonyl, a ketone like that, right? Because if I dotted that carbon right there, this carbon right here of the R group is going to be my star, the nucleophile, which would make this the new bond between them. New bond right here, right? And that means that to get to that point right there, the first step would have to be this MGBR, where that starred pink carbon here is attached to the MGBR to become negatively charged, right? Which is going to attack this carbon, pop the double bond onto the oxygen, and create the O minus right there. And the MGBR is going to dissolve in the solution. So when we get the O minus, we could bring in a second step of H3O plus to protonate the O minus into an OH right here. Right. So that's going backwards, right? This is retrosynthesis. We are going backwards by predicting what this final product came from in the last step, right? I'm saying that this alcohol here came from that carbonyl right there, where this pink dot carbon here is this pink dot carbon right here, right? And I'm saying that this new R group that we added is this new R group right here, which when it attacks, it would attach that way, right? Like when the star attacks the dot, pop to the bonds to oxygen, it would be connected like this on the product. Right? Does that make
But
sense? Uh-huh.
yeah, so
Uh-huh.
we assume that because we have an OH that we know there's like there's uh, deprotonation,
Mm-hmm.
right?
Yep.
Um,
Uh-huh.
and then like basically we know that like the step before that, like we kick off the double bond that's there, right?
Yep.
Which is what you're saying, the carbonyl group.
Yep. Right.
I am a bit confused with the MGBR
Yeah.
though.
So the MGBR, whenever you see an atom attached to that, a carbon attached to that, like this carbon here directly attached to the magnesium, the charge of that is partial negative charge. Right. So I'm gonna draw out the mechanism here for you. Like this RMGBR here, the carbon directly attached to the magnesium is gonna be partial negative charge. This is the carbonyl that we said we had earlier. This carbonyl carbon here is partial positive charge. So this Grignard reagent here would be considered our nucleophile, the negative charge, and this carbonyl carbon here would be our electrophile, the positive charge, right? And in OChem, the nucleophile would always attack the electrophile, but when that happens, that's going to break the octet row, right? Because we're trying to make a new bond between the star and dot right here, but that's going to have 5 bonds on that dot carbon, 1, 2, 3, 4, 5, right? So what we have to do to conserve the octet row is pop the double bond onto the oxygen, and this MGBR here will dissolve in the solution. It just goes away. It dissolves into ions, right? So if I draw out the pink dot right here, which is this pink dot structure right there, it was double bonded to an oxygen, but now it is single bonded to an O minus. And then I'm going to draw it in the way that they drew in the product. This dot carbon is now bonded to a starred carbon, right? Making this the new bond that we made between them. And now when we look at what is attached to the star carbon, it is a methyl group, which is going to be this methyl group right there, right? Does that make sense so far on like how this Grignard reagent, RMGBR, attacked this carbonyl ketone to get this intermediate here?
Yeah, it
Right.
does.
So once we got this intermediate here, which added a new carbon-carbon bond, and we have an O minus from the carbonyl, now we bring in the second step, the acid workup step, H3O plus step. This O minus here is going to grab one of the hydrogens of the H3O plus and kick out the water, right, in acid-base reaction to neutralize and protonate the O minus to become OH right here. And water is going to be our side product right there, right? Which is why this is our final answer here, right? So whenever in the product you see a alcohol and a new carbon-carbon bond, always think of a Grignard reagent happening here, right?
Okay, that makes sense.
Yeah. So that's why when we go backwards here, I see an alcohol. The alcohol is attached to this carbon here, which is going to be the carbonyl carbon. This right here would be the disconnection we make to figure out what the Grignard reagent is, which if this is our star, that star would have to be attached to the MGBR to make it negatively charged like that, right? So that's going backwards. Now, our first step here is going to add a bromine to that second carbon, but now we have to figure out how to convert this bromine into, let's say, an alcohol, right? And that's going to be, let's see here. Yeah. Since this was a secondary substrate right here, to make this into alcohol, you would have to use some. Oh yeah, I see it. I see the functional group. Um, so this one right here, I don't know if Wei went over this, but Levens did, and she went over it like briefly. But when you try to convert a secondary substrate into alcohol, right there, you cannot use NaOH and water, right? That would not create that secondary alcohol because like this OH minus is a strong base that's going to do E2 instead. So what you're going to get instead is this Zaitsev alkene, right? Where the OH minus strong base is going to grab that most substituted hydrogen, make a double bond here, and kick out that leaving group, E2 reaction, right? So this is not going to do SN2, not SN2, because we have a secondary substrate, a small strong base hydroxide ion, which is going to be the E2 reaction, not SN2. But there is a way to make that bromine into an alcohol still, which is going to do SN2 with acetate, right? Which is going to be something like this, which is a weak base, strong nucleophile. It's a strong nucleophile because it has a full negative charge, but it's a weak base because it could do resonance with the carbonyl. This negative charge here could do resonance with the carbonyl. And would that make it more or less stable if we could do resonance?
It would be unstable
More stable, more
or
stable.
more stable. Okay.
Right. Because more resonance means that the electrons are more delocalized, making it more breathing room. Right. Think of it as like this electrons here as having more breathing room, making it more stable. And because it's more stable, it's gonna be less reactive, right? Less reactive, weaker base. So this carboxylate here is able to attack that carbon and kick out the leaving group to do an SN2 reaction. And when we do that SN2 reaction right here, we're gonna get this intermediate like this, right? Where this functional group here is an ester, right? And then this is a 118Z reaction here. When you react that ester with like uh, acid or base, you're gonna hydrolyze that into a carboxylic acid and alcohol. So the reagent that you might see here is, let's see, what is it? Yeah, you might see first step NaOH, water, second step H3O plus, or just H2O plus, right? Either one would work, but I'll check the key to see what they want under the question. That's going to create the alcohol, and the side product here is going to be this carboxylic acid, but that's going to be a 118C reaction, right? So this reaction here that I just did is going to be ester hydrolysis. Did Wei go over this type of reaction? When you have an ester, you can convert it into a alcohol and carboxylic acid.
She probably has, but uh, it's still confusing to
Right.
me.
So to make it like more clear on how to predict the product, this is the ester here. We're just gonna cleave that bond right there between the carbon, no carbon, and oxygen, right? And when that gets cleaved, this part here is gonna be our alcohol part. That yellow highlighted part is gonna be this part right here, right? This is just predicting the product quickly. Don't worry about the mechanism because the mechanism is gonna be covered in 118C. Um, the other part, which is going to be highlighted in pink, let's say, right here, is going to be this part right here. Right, right here. And then this OH group is just going to be coming from water right here. Okay. And then once we have that, do you remember how we could convert this secondary alcohol into a carbonyl right here?
Um,
Are we going to oxidize or reduce?
we want to reduce. I mean, oxidize,
Um,
sorry.
Oxidize, right? Because
Yeah, because it's losing the hydrogen.
yeah, it's losing this hydrogen and gaining a bond to oxygen, right?
Right.
It's getting a bond to oxygen, which is oxidation. So we could use either oxidizing agent, PCC or Jones zero. It doesn't matter because this is a secondary alcohol. You could use either
Right.
PCC or Jones to get the ketone.
Ketone.
Yeah. So let's use PCC, and it's a product solvent CH2CO2. Right. So synthesis problems here is going to give you the reactant and the product. And then the problem is going to ask you what reactions in the middle would um, convert that reactant into the product here, right? And then there were, let's say, over here, 5 reactions that we did. The first one was hydrogenation or reduction. The second one is bromination or free radical halogenation. The third one is SN2. fourth one is ester hydrolysis, and the fifth one is oxidation. And all of these reactions in sequence would convert this reactant into that product here, right? And there's a lot of strategies to do the synthesis problem. Like the first strategy I would look is what is my similarities between this reactant molecule and product molecule, which is that like 4-carbon chain right there, right? Which we have to open it up to get that right here. And then I see the differences between the reactant molecule and product molecule, which is the alcohol and the new R group. And then I think to myself, what reactions can add that alcohol and R group? And then from there, I try to go backwards and forwards and meet in the middle for synthesis, right? And there's more like patterns that you can look out for, but this is how I would do this type of problem here. This one's for epoxide opening, uh, as well, but this is how I would do it here. Like I go backwards. I remember when I first started this problem, I tried to make this into a Grignard reagent, but then I realized that that wouldn't work because that would make this the star carbon, and the alcohol would go away. And there is another thing that would like make this a little bit different as well. But does this make sense so far on like how I converted this reactant into this product molecule here with these reactions?
Yeah, so you said
Huh?
that we don't use the Grignard reagent
Yeah.
because if we do, I mean,
Uh-huh.
we use Grignard reagent
Uh-huh.
when we have a
Mhm.
C double C bond. I mean C double
Uh,
bond O, sorry.
when we yeah, when you have a C double bond O, that's gonna react with the C double bond O. But you know that you're gonna use a Grignard reagent. The most important key takeaway here is that you know that a Grignard reaction is gonna happen if you see a new carbon-carbon bond, right? On the molecule. If you see new carbon-carbon bond, then that's a big signifier, big key for Grignard reaction. Grignard reaction. And then I could show during the in-person review session or tomorrow's office hours as well on the differences between like if your reactant molecule is going to be the Grignard reagent or if your reagent is going to be the Grignard reagent. Because in this specific problem right here, our Grignard reagent is the reagent. We just brought that in out of like the lab or something like that, right? But sometimes your Grignard reagent would be coming from like the reactant, which to make that into Grignard reagent, you would have to put magnesium in there. And then there's ways to tell like when you would do what, right? In this case, what we had to do is bring in the Grignard reagent outside as a reagent, right? And that's because we see that this carbon here had an alcohol and this new R group right here, which that new R group is the Grignard reagent. And whenever you see an alcohol, the carbon directly attached to the alcohol is going to be the carbonyl carbon right there. So that's why this original reactant here could not be the Grignard reagent. It had to be the carbonyl that the Grignard attacks right there because of the alcohol distance from that substrate carbon. If the alcohol was like 1 carbon away or 2 carbons away, then that would be a different story.
Okay.
Right. And I'll
I
show you
think
that
that
like
makes
different
sense.
scenarios like soon. It's like tomorrow probably tomorrow or the in person final review session. Yeah.
Okay.
Uh-huh. Yeah. Okay. So now let's do one HNMR problem. Kathy, did you have any HNMR uh things you want us to go over? Okay. So what I'm gonna do is I'm gonna do compound B or compound C. Which one do you want me to do? Because these HNMR problems take like a pretty long time to do. Compound B or compound C? Which one is harder? Let's see. Compound. Yeah. Let's do compound C. Let's do compound C. Let's see here. Let's see. Compound C. Mhm, mhm. Okay. So the first thing I always do for all spectroscopy problems is calculate the degree of unsaturation, DOU. And the equation for that is 2C plus 2 minus H minus X plus N all over 2. And the chemical equation is going to be given here, which is C10H20O2, right? C10H20O2. So when we calculate the degree of unsaturation, that's going to be 2 times 10 plus 2 minus 20 minus 0 because we have 0 halogens plus 0 because we have 0 nitrogens all over 2. And that's going to be 20 plus 2, that's 22. 22 minus 20, that is 2, right? Yeah, 2. 2 divided by 2 is 1. So we have 1 degree of unsaturation. And a degree of unsaturation is going to represent how many double bonds, triple bonds, or rings that you have. Right. So one double bond is going to represent 1 degree of unsaturation. One triple bond is going to represent 2 degrees of unsaturation. And one ring is going to represent 1 degree of unsaturation. And they add up, right? Because let's say, for example, you had a molecule that had a benzene ring. This benzene ring will have 4 degrees of unsaturation because there's 3 double bonds, 1, 2, 3, and 1 ring. 3 plus 1 is 4 degrees of unsaturation, right? So in this molecule here, we have 1 degree of unsaturation. So that could mean that we have a double bond or we have a ring in the molecule, right? We cannot have an alkyne, right? Because an alkyne will have at least 2 DOUs, but we only have 1 DOU here. So we either have a double bond or a ring. And then we could figure that out using the IR, right? So that's the next thing I look at. Let's look at the IR now, which is going to tell you what functional groups are present. Have you memorized the IR chart, Kathy? Not memorized, yeah. But do you have my IR chart, like of what I think about in IR? I think it's somewhere here. Right here. Yeah. So this is the IR chart that I think about. It, for Farhat, since he doesn't like allow note card, I would memorize these peaks that are important for IR. Right. So if I look at the IR here, I see a sharp peak at around 1700, right? Which would represent a carbonyl peak, a carbon double bond oxygen peak, right? Um, this 3000 peak right here is going to be regular sp3 carbon hydrogen peak, so we could ignore that. This is going to be the 1500 fingerprint region, so we ignore that. So the most important information we get from the IR is going to be this sharp peak here, which is around 1700, 1750, and that represents a carbon double bond oxygen group. Right, so that's going to be where our DOU comes from. This 1 DOU that we calculated earlier is going to come from a carbonyl, carbon double bond oxygen. So now we know that we will not have a ring, right? Because our 1 DOU will come from a carbon double bond oxygen, like that. Right. Okay. So now let's look at the HNMR here. The next thing is I look at the HNMR. IR, we have a carbonyl, HNMR, and then we piece the fragments together. So this 9 hydrogen peak right here, how many neighbors would these 9 hydrogens have if it has 1 subpeak? 0 neighbors, right? And whenever you see this 9 hydrogen with 0 neighbors, it's most likely going to be this fragment right here in the molecule, right? This squiggly line here is showing a fragment of the molecule, right? Like if our molecule was this, like for example, that molecule has this group attached to it, that tert-butyl group attached to it. I don't know what is attached to the rest of the molecule yet, but I know that one part or one fragment of the molecule is going to be this tert-butyl group right here, right? Because that tert-butyl group with its 9 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens right here, it's going to be these nine hydrogens right here with 0 neighbors, right? Because if we go start with 1 hydrogen and we go 3 bonds away, 1, 2, let's see here, 1, 2, 3, there's no hydrogen there, right? Or 3, that should be no hydrogen. That should be a carbon, right? Does that make sense? Yeah. Okay. Wait, I'm gonna be right back. I'm gonna get a paper towel really quick. Okay, I'm back. So this is the third butyl group we have right here, and it is in the shielded region because it is at the right side, right? Are you familiar with the shielded versus de-shielded region? Like if it's more to the right, it's shielded. It's more to the left, it's de-shielded, and what that means? Yeah. Okay. So de-shielded is going to be like these groups here are next to electronegative atoms, next to electron withdrawing groups, right? So let's look at these 6 hydrogens now. How many neighbors do those 6 hydrogens have? One neighbor, right? And I'm gonna represent that as this right here, this fragment, where those 6 hydrogens right here are gonna be these 6 pink hydrogens, 1, 2, 3, 4, 5, 6, which are these 6 pink hydrogens right here. And its one neighbor is gonna be this one neighbor right here, one hydrogen right there, right? So this one hydrogen right here, I'm gonna say that is this peak right here with one hydrogen. And how many neighbors would that one hydrogen have if it has 1, 2, 3, 4, 5, 6, 7, 8, 9 subpeaks? 8 neighbors, right? Do you see 6 neighbors already right here? Yes. So that means how many neighbors does it need left? 2 more, right? So I'm going to expand the fragment here, erase that squiggly line, expand it, put that squiggly line right there. And I'm going to say that its 2 other neighbors are these 2 hydrogens right here. Does that make sense? Yeah. So those 2 hydrogens right there, I'm going to say is going to be these 2 hydrogens right here, right? If those are my 2 hydrogens right there, how many neighbors would these 2 hydrogens have? 3, right? Because there's 4 subpeaks, 1, 2, 3, 4. But right now, how many neighbors does it have? Like as it's drawn out right here. 1. So how many neighbors does it need left? 2. Yes, you're right. 2, right. Which is going to be represented like uh this right here. 2. And I'm going to represent that as these 2 hydrogens right here. Which the only other peak with 2 hydrogens is this one right here. But you know how these 2 hydrogens right here is like very to the left side, de-shielded between 3 to 4 range? What does that mean? What does that mean like if these 2 hydrogens are between 3 to 4? Next to an electronegative atom. What electronegative atom do we have on the chemical formula? Oxygen. So I'm going to put an oxygen right here, right next to that 2 hydrogens because it is going to make it de-shielded between 3 to 4. Right? Does that make sense? Yeah. So to make sure though, how many neighbors should those 2 hydrogens have with 3 subpeaks? 2. Do these 2 hydrogens have 2 neighbors right now as it's drawn? Yes, it does. That's good. Okay. So we used up 1 oxygen, right? But we still have 1 more oxygen. And you know how in the IR we figured out that we had a carbonyl? I didn't use that carbonyl yet. So we have a carbonyl somewhere, and we have a tert-butyl somewhere still, like from this peak right here. So what I'm gonna do is that I'm just gonna guess, right, that this is an ester, like that. I'm just gonna put the carbonyl right here to the oxygen, making this an ester. Because whenever I see two oxygens like that, a lot of the times, the unknown compound has an ester like that, right? And that just came with like practice. Not all of the time though, because I've seen some where the carbonyl is right here, and then this is not an ester, but they made like an ether, right? But most of the times that this is an ester, and that would satisfy the carbonyl, carbon double bond oxygen part of the IR. Does that make sense? That was just a guess, but we'll double check later. Now, this butyl group here, I'm just going to slap it on here at this part of the molecule. Does that make sense? Yeah. So now let's verify with the chemical compound. 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. 20 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 hydrogens. That's good. 2 oxygens, 1, 2. That's good. Right. The IR, we have the carbonyl. That's good. DOU, there's 1 DOU. There's 1 double bond here. That's good. The H and the R, everything makes sense, right? Everything pieces together. Our butyl group here for that 9 hydrogen peak is that one. And then all of these color-coded hydrogens are these color-coded peaks right here. Right. Yeah, so it's mostly like guessing, like trial and error. When you first start doing these practice problems, your guesses will be slower and you're gonna mess up a lot with like, and you're gonna do more trials, like, and then you're gonna have to try over again until you get the right structure. but as you do more practice, you're gonna get more like patterns, more intuition of what the molecule would look like, right? And you have to verify with everything, alchemical formula, IR, HNMR, DOU, to verify that this is the exact structure of the unknown structure. Yeah. So this NMR problem here is going to require the most amount of practice to get used to, right? This and synthesis probably. Yeah, spectroscopy and synthesis. But the reactions, predicted products, and mechanism, that's more straightforward, more easy to pick up. And nomenclature, yeah. Okay. So now let's move on to 118C. Camilla, you wanted to go over. Let's see. Cycloaddition reactions
Yeah.
and non-aromatic heterocycles reactivity. Okay.
Yes, please. Also, I don't know if the picture's like a quick one, but I
Uh-huh.
just didn't know why it didn't go to the meta position.
Yeah. So this is a thiophene right here, a 5-membered heterocycle, where the hetero atom here is sulfur. And when we react that with Br2, wait, this had a bromine on it as well. The answer, put the bromine on the highlighted carbon right here.
Yeah.
Like, right, okay. Yeah.
Or I thought it was there. I don't know.
Oh,
It's not, though.
you put that there, but it was not correct?
Yeah.
Okay.
But I wasn't sure. I don't know. I've been watching Joe Cam
Oh, yeah, Dokam?
what
Yeah.
to do, so I was like, oh.
I know. He's very like good at explaining things conceptually. Okay. Um, so this sulfur here has 2 pairs of electrons. When we do resonance right here, we're gonna get these resonance structures here. Let's see here. Sulfur. Oh, wait, I'm gonna do resonance with a regular thiophene with no groups attached to it to see what resonance structures I would get. You get that negative charge. That negative charge. And this negative charge. Just making sure here. Of style. Yeah, negative charge there, and there. Okay. Yeah, so there would be a negative charge everywhere besides the heteroatom. Yeah, and then we can even go down there, make a negative charge there. And that would put negative charges on every atom except the sulfur. Yeah, right. Yeah, negative charge here, 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 and here. Boom, boom. Okay, yeah. So wait, let me see his lecture notes to see how he taught this. Lecture notes, heterocycles, platform. Oh, I see, I see, yeah, yeah. So the resonance structures of the current structure, does that make sense? We're trying to look at the resonance structures of the intermediate when we add the electrophile. Okay. So usually when we do electrophilic aromatic substitution, we attack C2. These carbons right here next to the sulfur, because that would lead to the more stable intermediate with more resonance structures. Right. So ignore the resonance structures here. That would not affect the EAS reaction. What would affect it is the intermediate uh, um, stability. Right. So BR, BR, check that, take that out, get this intermediate. To get that bromine, positive charge here, bromine here. Means we could do resonance like this, making it positive charge. Oh, I see what's going on here. Here. And then that can be stabilized by that. Positive charge, bromine. Okay. And they said that this was not the right answer, right? Like adding that bromine here, not the right answer.
Yeah, they said it wasn't right. But I think in
Okay.
the chat, someone said it was C2.
C2, yeah, this is C2. What if we attacked this side right here? That would add a positive charge here, which when we do resonance, we're going to get the same thing. I'm just going to draw it out like this. Right? The resonance set in pink would be more stable than the resonance set in black. Right? Because the positive charge here is stabilized by this bromine right here. Right? Because that bromine can donate one of its pairs of electrons directly onto that carbocation right there, making it more stable. Whereas if you look at the bromine on the black resonance structures, you cannot stabilize the carbocation directly, like this bromine here is. Right. So the answer here should be this C2 next to the bromine, ortho to the bromine, because that would lead to this more stable carbocation intermediate.
So in general, when I'm given a problem like this, do I always have to draw out the resonance structures?
Um,
Or
to
like, how do you know fast? Like, where do you add?
yeah, how do you know fast where to add? At the beginning, you would have to draw the resonance structures like this, and then to know quickly, you could try visualizing the resonance structures in your head and see which resonance structures will give you the most stable structure.
Okay, I don't know if this is right, but on Jochem, he was saying something about how it always adds on C2. Is that actually right?
Uh, it could also add on C3 as well, but
Okay,
major
yeah,
product will come from C2.
yeah. So is that a good rule to like
Uh-huh.
follow?
Yeah, that is a good rule to follow. But if you have a substituent on the ring like this, like that can do resonance, then you would put it on the C2 that is closest to the group.
Okay, so
Uh,
C2 first and then C3.
yeah, C2 first and then C3.
Okay.
This is still C2, but it's at the C2 closer to the substituent, the other substituent.
Okay.
Yeah,
Okay.
yeah,
Thank you.
yeah, no problem. Okay. Yeah. So I think I'm gonna end office hours early tonight. I think I'm feeling like a little sick right now. But I'll see you guys tomorrow in office hours, and I'm gonna get some rest early, and I'll see you guys tomorrow and in person on Saturday. Yeah.
No worries.
Huh?
Hope you feel better.
Yeah. Thank you. Thank you.
Thank you so much.
Yeah, no problem. Yeah, good luck, guys. See ya. Bye.